Said, my name is Marcelo Bruno, and I'll be talking today about some ideas for manifold constrained distributed particle filtering. And just as a disclaimer, most of the work here was done actually by Claudio Borgini, who was my previous postdoc, now a professor at the Federal University of Santander. And there is also some work done by my former student, Caio Figueiredo. So just to give you some motivation, in several real-world applications, like in robotics, in attitude estimation, computer vision, or machine learning, the hidden state variables of interest, they naturally lie on non-Euclidean spaces. And the filtering methods that ignore the geometric constraints on the state space and just make inference as if the states were Euclidean, they tend in general to perform not so well. So because of that, there has been a lot of work over the past years to incorporate geometric constraints into the design of filters. So here I have a couple of references of people who looked at designing filters, in particular manifolds such as matrix Lie groups, unit spheres, or more generically Stifel manifolds, of which the unit sphere is a particular case. Some of those methods implement the filters using sequential Monte Carlo techniques. Others use more parametric type techniques, so they are in essence manifold constrained Kalman type filters. And in this particular talk, I'll talk about sequential Monte Carlo implementations for manifold constrained Bayesian filters, but in a distributed context. So in this distributed context, we have multiple observers, which are located on remote nodes of a partially connected network. And those multiple observers using only local communications within the network neighborhoods, they want to cooperate to track a single hidden state sequence that is evolving on the manifold. So basically, first I'll give you some background on existing methods on distributed Bayesian filtering. So here I'm not going to talk about any new SMC method. I'm just going to describe existing distributed Bayesian filters. Then I'm going to show how to adapt those existing methods to handle states now that are defined on manifolds. In order to do that, I have to provide some background on some basic tools on manifold geometry. And after I provide this background, I'll move on to describe specific designs for distributed particle filters on matrix Lie groups, then on L spheres, hyperdimensional spheres, and finally on the Stifel manifolds. And then I'll present some numerical results and offer some conclusions. Okay, so just to explain the framework, we have here the framework for distributed Bayesian filtering. We have a single hidden sequence of states, S sub k, that's evolving in some space M. And as I said, we have multiple receivers that are dispersed over a partially connected network. And each observation lies on a certain node R of this network of capital R nodes. And the nodes have access only to their local observations or to the observations at their neighbors according to the topology of the network. So it's a partially connected network, basically. And I'm assuming the usual conditional independence hypothesis. So given the current state, I'm assuming that the observations at node R are independent of the observations at all other nodes S, even at the same time, and are also independent of all the previous observations from instant 1 up to instant k minus 1 over the entire network. And I'm also assuming that given the previous state sk minus 1, the current state sk is independent of s1 k minus 2, and also independent of all the previous observations from 1 to k minus 1 over, again, the entire network. If I had a centralized architecture with a data fusion center, the data fusion center connected to all nodes in the network, the data fusion center could receive all the measurements from each of the nodes and then stack all those measurements in an extended observation vector and run in a centralized way the optimal Bayesian filter. So the optimal Bayesian filter would compute then the posterior probability density function of the current state given all the observations from 1 up to k and collected over the entire network. So you would do prediction according to the transition PDF, and then it would update the predicted posterior using the likelihood of the observation of the extended observation factor, which in this case factors as the products of the likelihoods of the local observations, because they are conditionally independent given the states. The problem is that if you are on a partially connected network, you don't have a data fusion center, there is no obvious way of computing these products over all nodes R. It could be done in a fully distributed fashion if you ran, for example, some sort of consensus algorithm over the network. But those consensus algorithms, they require normally multiple message passing between nodes during the time period between two consecutive measurements. So they are very time consuming. Normally they are not they are badly fitted for online applications. And because of that, what people do in practice is to use some kind of suboptimal filter that is fully distributed and has low internode communication costs. So here I'm going to review basically two schemes that have been used for some time, about 10 or 15 years. The first of them is what's called, adapt then combine filtering, or ATC filtering. And here I have some references of people who either proposed this method or analyzed this method theoretically. And basically what ATC does, it has two steps. One step is an adapt step, where let's assume that at instant k-1, node R has this posterior piece of k-1 given k-1 for the state sk-1. So at the adapt step, each of the nodes independently run a local Bayesian filter, assimilating only the local observations. So basically, this is exactly like the optimal filter that we've seen before, except that the products now is not over all the nodes of the network, but only over the nodes that are in the closed neighborhood of R. So basically, you take the local posterior, do a prediction, and then you assimilate the measurements at the same node and at the neighboring nodes. And after that, you get a locally updated posterior. So this is done independently at each node. So there is no communication outside the local neighborhoods. Once you have this those updated local posteriors, you now have a combined step where you merge or fuse those local posteriors in local neighborhoods. And there are different kinds of fusion techniques, but the most common fusion technique is just to replace the updated P at node R by the geometric average of the posteriors that are in the neighborhood. So basically you have this weighted geometric average here with certain combination coefficients A sub RU. And it's well known that after normalization, the PDF that you get using this geometric average fusion is the PDFP that minimizes this weighted average KL divergence between P and all the functions P sub KU that are in the neighborhood of R. If you are in a sequential Monte Carlo setting, if you have now weighted particle set representation for this local posterior, you can now, given the model in this local Bayesian filter, you can generate now an updated particle set for the locally updated posterior. And in this case, you can use any SMC method that you like to do that. And in this particular case, I just used the simple marginal particle filter, but it doesn't matter. And then you have to do the combination. And instead of working with the particles to make this combination computationally efficient, what practitioners normally do is to take the updated particle sets and fit the updated particle sets to a certain parametric approximation with a number of parameters that is smaller than the number of particles. And typically, you would like to fit it to a function of the exponential family, because that allows you to compute the geometric average fusion in a closed form solution. And the easiest thing, if you are working with Gaussian states, the easiest thing would be just to compute the conditional mean and conditional covariance, and adjust the particle set to a Gaussian. And if each of those terms is Gaussian, then the geometric average is also Gaussian, and you can compute the fused mean and the fused covariance using the conventional covariance intersection equations, which we have seen this week in another talk, I think, maybe yesterday. The problem is that, of course, if you have states that are not on Euclidean space now, you cannot do this because you cannot adjust the particles that are on the manifold to a Gaussian, because the Gaussian does not represent points that are on the manifold. So basically, this is the ATC filter. And then there is another technique that's very much used by practitioners, which are the so-called random exchange or gossiping filters. So the random exchange filters, contrary to the ATC filter, instead of having an adapt step and a combined step, they have a random exchange step followed by a data simulation step. So in the random exchange step, if node L has a posterior at instant k minus 1, node L chooses a random neighbor S, and nodes L and S exchange their posteriors. So the posterior from L goes to S, and the posterior from S goes to L. And then S chooses another neighbor R, and it sends its posterior to R. And this asynchronous exchange process continues until it stops. And when it stops, the posterior that was originally at node L ends up in some random node R, which is not necessarily located in the immediate neighborhood of L. So basically, there is a random exchange where you send each node sends its posterior to another node in the network, and the exchange is only used local communication, but because they are connected, it may end up in a more remote node that is not in the immediate neighborhood. And if the posterior is represented by particles, theoretically, to do this exchange, you would have to transmit all the particles over the network, because that's the representation for the posterior. Of course, you don't want to do that, because transmitting particles over the network has a very high communication cost, because the number of particles is normally very high. So again, instead of transmitting the particles and the weights, you try to fit a parametric representation to the weighted particle sets, and you just transmit the parameters of this representation. And once node R receives that parametric representation, node R then resamples from the parametric representation and restores at node R the particle set that was originally as node L. And then in the data simulation step, node R runs a local base filter using as input the particles from the remote nodes. So now you update this posterior here using the local observations that are around node R at instant k. And what you get in the end is a representation now for the posterior of S, given the previous measurements that had been assimilated by node L up to instant k minus 1, plus the new measurements around node R that have been assimilated now at instant k. So basically, what this method is doing is the random exchanges are drawing random paths on the graph. And each node at instant k is the end point of one of those random paths, let's say I sub k. And the path starts at I0 at instant 0, I1 at instant 1, I2 at instant 2, and so on up to Ik at instant k. So the posterior you get at node Ik at instant k is the posterior condition on the measurements that were assimilated around I0 at instant 0, around I1 at instant 1, around I2 at instant 2, and so on, around Ik at instant k. So each node has a different posterior conditioned on a random subset of the set of all measurements in the network. And this random subset changes from node to node. And basically, that's what's called random exchange or gossiping. So my goal in this talk is actually to show how to adapt those methods to handle now states that are defined on non-Euclidean spaces. And for that, I have to give you some background on geometry. So basically, the idea here is that a manifold can be locally approximated at each point P by its tangent space T sub P, where T sub P is now an Euclidean vector space. So for example, if you have a unit sphere, you can define a tangent, you can define a tangent space at each point at each point S, at each point P, which is basically the left null space of P. So the unit sphere is the set of all S's such that the norm of S is equal to 1, and the tangent space at P is just the set of all vectors V such that P transpose times V is equal to 0. So it's just the left null space of P. In a general Stiefel manifold, which is defined now as the set of all n times m matrices with orthonormal columns, the tangent space at matrix V is at matrix S, sorry, is the set of all matrices V such that S transpose times V is skew symmetric. And again, if you make m equal to 1, you see that the unit sphere is a particular case of the Stiefel manifold when m is equal to 1. And when m is equal to 1, S transpose times V is in scalar. And this equality here reduces to S transpose V equals to 0, which is exactly the tangent space of the sphere, right? So basically, the sphere is a particular case of the Stiefel. And for our talk, what's important here is this operator called the exponential map that allows you to, given a certain vector V at the tangent space at point P, it allows you to map this vector V to a certain point on the manifold such that the norm of V is equal to the geodesic distance between the tangent point and the exponential map of V at P. So basically, it's a mapping between the tangent space and the manifold that preserves distances. So the norm of V here is equal to the length of this curve, okay, when you do the projection. And the inverse of this operation is the log map. The log map now goes from a point on the manifold to a point on the tangent space. And another tool that we are going to use is the parallel transport, which is an operator that allows you to move vectors between tangent spaces. So the parallel transport, given a vector that is now in T sub P, it allows you to move to a vector in T sub Q and at another point on the manifold, preserving inner products. So the norm here of VT0 is equal to the norm of VT1. So for example, for the L sphere, if you want to draw the geodesic curve between S and a certain point S tilde, which is in the vicinity of S, you just compute the log map of S tilde at S, and then the geodesic will be this great circle here, such that gamma of 0 is the tangent point S, and the derivative gamma dot of T evaluated at 0 is equal to V. So V is basically like the velocity of the geodesic in this case. And then the exponential map is just this geodesic computed at T equal to 1. It has this form here. And then you have the inverse log map. And then the geodesic distance is just the norm of the log map, which is in this case is the arc cosine of S transpose times S tilde. It's actually more intuitive to see in the matrix Lie group. So the matrix Lie groups are matrix groups. They are closed with respect to matrix multiplication and matrix inversion. There are also manifolds. So for each matrix in the matrix Lie group, you can also define a tangent space. For example, you can have the special orthogonal group, which is the group of all orthogonal or square orthogonal matrices that have determinant equal to 1. And you can also define the special Euclidean group, which has elements that consist here of an orthogonal matrix and here of a real vector. And this special orthogonal group can, for n equal to 3, it can be used to model rotations in 3D space. And the special Euclidean group for n equal to 3 can be used to model rotations and translations of rigid bodies also in 3 dimensions. And in particular, the tangent space at the identity is the Lie algebra of the matrix Lie group. And it turns out that the exponential map and the logarithmic map at the identity have very simple expressions. The exponential map at the identity is just the standard matrix exponential function. And the exponential in the log map at the identity is just the standard matrix log function. And so basically you have this picture here that shows what I'm talking about. So here you have the manifold, and here you have the identity, and here you have the tangent space at the identity, which is the Lie algebra. And using the log function, you can go from the manifolds to the Lie algebra, and using the exp function, you can go from the Lie algebra back to the manifold. And because the manifold is a vector space, you can also find a basis for the Lie algebra, and you can represent each point on the Lie algebra by the coordinates of this point in the basis that parameterizes the Lie algebra. So there is a one-to-one correspondence, bijective mapping between the Lie algebra and the Euclidean space Rg, where G is the dimension of the Lie algebra. And that's actually what we're going to do later. That's actually what we're going to use later to design the particle filter. So we're going to use this mapping from the manifold to the Lie algebra, and then from the Lie algebra to this coordinate space, basically. So just to give you an example how this bijective mapping works, like in a practical situation, if you are in the special orthogonal group, the points in the Lie algebra are the matrix log of orthogonal matrices, and the matrix log of orthogonal matrices are skew symmetric matrices. So for n equal to 3, they are parameterized only by free parameters. So there is a correspondence between each point in the Lie algebra and a point in R3. If you are in the special Euclidean group, the log map of a matrix like this has an upper left corner, which is also a skew symmetric matrix. And it has here a real vector. So now it's parameterized by 6 free parameters. So you have 3 parameters to parameterize the skew symmetric matrix, and another 3 parameters to parameterize this column vector here. And now there is a correspondence between each point in the Lie algebra and one point in R6. In general, if you have an arbitrary point S in the Lie group, the tangent space is the set of all matrices that have the form S times X, where X is in the Lie algebra. And using this parameterization, it's easy to see that you can move from one tangent space at S to another tangent space at S tilde, doing simply this operation S tilde times S minus 1 times V. Basically, because when you do S minus 1 times V, you recover X. And then this product now has the form S tilde times X, which is now in T sub S tilde. So the transport between tangent spaces is very simple in the matrix Lie group. And using this intuition, it's also very simple to understand how the log map and the X map work at the generic tangent points. For example, suppose that you have S tilde, which is in the vicinity of S. It's close to S. First, you multiply S tilde by S transpose, then you move it close to the identity. Because if S tilde is close to S, S transpose times S tilde is close to the identity. At the identity, you can approximate this point by a point in the Lie algebra using just the standard log operation. So now you have a point which is in the Lie algebra, it's at the tangent space at the identity, and you multiply by S, and you move it to the tangent space at S. And this is the log map of S tilde at S. The exponential map is exactly the opposite, the reverse operation. So if you have F, which is S times X, you multiply by S transpose to get a point X in the Lie algebra. This point X in the Lie algebra, you can move back to the manifold using the matrix X exponential function. Now it's a point on the manifold close to the identity. Then you multiply by S to bring it close back to S. And it's just this. It's very simple. And all the geodesic curves that pass through S and connect S to S tilde have this form X sub S of V times T, where V is the log map. And you can see here that the derivative of gamma is equal to V at 0. And again, the gamma at 0 is equal to S. And you can also see that gamma dot is in T sub gamma for all T's. So the derivative is on the tangent plane for all times T along the curve, which is a property of the geodesic that gives you the minimum distance between 2 points. And the geodesic distance in this case is just the norm of the log map, which here in the special orthogonal group is the Frobenius norm of the log of S transpose times S tilde. Well, what does this have to do with particle filters? How can I use this to design particle filters? So that's the point of the talk, right? Because so far I've only been talking about the geometry, nothing about particle filters. But anyway, so if you want to do distributed particle filter on a matrix Lie group, the first thing that you have to do is to define a dynamic space on the group. So here I'm considering a very simple dynamic model where I'm just moving randomly on the group. So how do I move randomly on the group? I want to draw, for example, a random walk on the group. So first I can sample this vector epsilon from the Gaussian distribution in Rg, where G is the dimension of the Lie algebra. And now I can map this set of coordinates, let's say, that I'm sampling RRG. I can map those coordinates to a matrix here in the Lie algebra using that bijective operation. So now this bracket here is on the Lie algebra. Then I multiply by sk minus 1 to move it to the tangent space at sk minus 1, where sk minus 1 is my current state. And now I compute the exponential map at sk minus 1, and that gives me a new point on the manifold, which is my new state sk. And I keep doing this, building tangent space at each sk, until I have this random path on the manifold. That's actually equivalent to generating, for example, in the special orthogonal group, generating random orthogonal matrices and multiplying those random orthogonal matrices by the previous state. Because the group is closed with respect to the multiplications, this multiplication will remain an orthogonal matrix. And for the observation here, I just have a nonlinear function. I'm allowing the observations in general to be matrices, right? So I have a nonlinear function of the current state, and I'm adding here some matrix Gaussian noise. So the observations themselves are lying on Euclidean space in this particular case. The states are on the manifold on the group, but the observations are on Euclidean space. And this model here defines a transition PDF on the group, which looks more or less like this. And it also defines a likelihood function here on Euclidean space, which is in this case is just matrix Gaussian. And now I want to do gossiping filtering, and I want to do ATC filtering for this particular state space model. So let's start with the gossiping, which is simpler to understand. Suppose that at instant k minus 1, I have a weighted set of particles that represents the posterior on the group, okay? So the first thing that I would like to do would be to compute the so-called intrinsic mean, which is the point on the group that minimizes the expected value of the geodesic distance between S and the true state sk minus 1. This intrinsic mean is like the equivalent on the manifold to the minimum mean square error, let's say, on Euclidean space. And if I have a Monte Carlo representation for the posterior of the states, you can approximate this expectation by this weighted sum here. And the problem reduces to finding the point on G that minimizes the weighted geodesic distance to each of the particles in the particle sets. So again, if instead of geodesic distance, I had Euclidean distance here, the solution to this problem would be just the weighted average of the samples, which is the estimate for the MMSE that's given by the particle filter. But because I'm on the manifold, I cannot just do a simple average because the manifold is nonlinear. And if I do an average, the average will fall outside the manifold. So I actually have to solve, numerically this problem to find the centroid of the particles on the group. And there are many ways of doing. One way of doing this is to do this sort of iterative steepest descent algorithm, where basically I choose one particular particle as the first candidate to be the centroid, and then I compute the log map of the particles at this candidate, and now they are all on the tangent space. And now I do an average on the tangent space. And once I average on the tangent space, I project back on the manifold using the exponential map. And the projected point is now my next candidate to be the centroid. And I keep doing this iteratively until it converges to some point, which is a local minima of this weighted sum. Okay, so this is called the Karcher mean, if you're familiar with Riemannian geometry, is what they call Karcher mean. It's like an average on the manifold. Okay, so now that I have this Karcher mean, what can I do? I can take the particle set and I can project all the particles on the particle set to the tangent space at the Karcher mean. So I build the log map at the Karcher mean. Okay, so now all those terms here lie on the tangent space to the Karcher mean. Then I multiply by the inverse of the centroids, and I move this to the Lie algebra. So now I have all the particles represented on the Lie algebra, represented on the tangent space at the identity. And those particles that are on the Lie algebra, I can map now to points, to coordinates in Euclidean space. In the Euclidean space Rg, where G is the dimension of the Lie algebra. So now I have a set of particles that is all expressed in the Euclidean space that is the embedding of the Lie algebra. And because now they are all in Euclidean space, I can fit to this particle set a Gaussian distribution, for example, a standard distribution that I would use for Gaussian states. And so that's what I do. I fit a Gaussian. And now I can transmit this Gaussian. I'm in the gossiping scheme here, right? So I can transmit this Gaussian from node L to node R. And when node R receives the Gaussian, it resamples from the Gaussian. And now, after it resamples from the Gaussian, it takes those points and bring them back to those points are coordinates, right? They bring them back to the Lie algebra using the bijective transformation, multiply by the centroids S hats to bring them back to the tangent space at S hats, and then do the exponential map to bring them back to the manifold. So now I restore that at the remote nodes a particle set which is around the original centroid S hats that came from node L. So basically, I have to transmit the parameters of the Gaussian, and I also have to transmit the centroids. But the communication cost is really very light. Doesn't have very. And now that I have the restored particle set, I can just run whatever particle filter I want on the manifold. In this particular case, I just ran a bootstrap particle filter. So I sampled now from the dynamic model on the manifold, and then I updated the weights using the product of the likelihoods. The likelihoods in this case are Gaussian because the observations lie on Gaussian space. And then the estimate, the final estimate for the state is just the Karcher mean of this set. If you want to do ATC, to do fusion, then first you have to do the local assimilation step. So the local assimilation step takes the input particles and propagates those particles using a particle filter. Here I'm using a marginal particle filter. And now, once I have the updated particle set, I can compute next the Karcher mean. And then I do exactly the same thing that I did before. I have the representation of the particles on the Lie algebra. I fit a Gaussian approximation to the approximation of the particles on the Lie algebra. And now I do the fusion of those Gaussian approximations using the geometric average fusion rule. Then I can resample from the fuse PDF. I can map the samples back to the Lie algebra. But now, instead of moving to the centroid at the local nodes, because I'm doing fusion, I move to the tangent space at the average of the centroids. So basically, I have the I have the centroids for each node U in the neighborhood, and I compute the average of those averages. So this is like the mean of the local centroids. And now the particles that have been sampled from the merged PDF and are on the Lie algebra are moved to the tangent space at this mean of the local means. And now I apply the exponential map at this point, and now I have a set of particles that are around the mean of the local means. So I'm doing two level fusions, right? So I'm doing a fusion on the location of the tangent spaces, and I'm doing a fusion also on the coordinates of the points at each of the tangent spaces. And then basically you do it. You can compute the final estimate using the Plotter mean. Okay, I can do the same for the L spheres or for the Stifel manifold, but in the L spheres or the Stifel manifold, instead of doing that random walk, I'm going to move the particles on the manifold using some kind of circular statistic. So here I'm using the von Mises-Fischer distribution. This is the expression for the von Mises-Fischer distribution for the sphere. And there is a generalization for the matrix generalization also for the Stifel manifold. And you can also use it, you could also use a Fischer-Binghen distribution, which is similar to the von Mises-Fischer distribution, except that you have this quadratic term also in addition to this linear term in the exponential. And hopefully for us, there are methods in the literature that will tell you how to draw samples from those circular statistics. So here I'm showing some references where they show samplers for the von Mises-Fischer and for the Fischer-Binghen distribution. So in my model now on the sphere, I sample S given sk minus 1 from a VMF on sk given sk minus 1. And now here I have an observation model. This one is a more concrete model that has a better, physical interpretation. So it's motivated by a problem in engineering where you have a frequency selective channel and you transmit a message over the channel and you get at the receiver the convolution between the channel coefficients and the message. So basically what you get is a linearly distorted version of the message that you transmitted with some additive noise. And a common problem in engineering is given a pilot, given a known input, and given the output, you want to identify the channel coefficients. So it's what's called supervised equalization or supervised channel identification. In this particular case, we have instead of having only one receiver, there is a network of receivers, a network of adaptive filters, if you will, and each filter is being trained by a different pilot sequence, but they are all tracking the same channel. And I want to estimate the channel cooperatively from the different observations at each receiver using the different training sequences. But there is a caveat here that because of automatic gain control at the receiver, the power at the output of the receiver has to be constant. And that translates into a constraint on the norm of the channel coefficients. So I'm doing the supervised identification subject to the constraint that the norm of the channel is constant. And without loss of generality, I'm assuming that this is equal to 1. So that's where the manifold restriction comes in, because I'm restricting the channel coefficients to have a constant norm. And it should make it a little bit more complicated. I'm also adding some pointwise nonlinearity here that can model nonlinearities at the receiver. And basically the matrix version of this for the Stifel manifold is similar. You have a transition PDF here using a matrix VMF. And then what you observe here is a matrix S multiplied by a matrix whose columns are different pilots. So you may think of a communication system that has one antenna and multiple receivers. And this is the channel matrix. And each row of the channel matrix is the channel between the transmitter and one of the receivers. And then the antenna sends L pilots, and you collect basically SK times this matrix of L pilots at the receiver R. Except that here I'm constraining S to be unitary, to be orthogonal matrix. So I'm not really estimating the channel, but I'm estimating the column space of the channel. So you can think of this as a subspace tracking problem, a supervised subspace tracking problem. It's exactly the same problem as before, but it's a matrix version of that problem. And the interesting thing here I don't have much time, but in the Stifel manifold, the interesting thing is how to parameterize the points on the tangent space. So basically, I mentioned to you before that the points on the tangent space to the Stifel are those vectors, those matrices X, such that X transpose times M is skew symmetric, right? So in general, you can parameterize those points as M times A plus M perp times B, where M here is, where A here is M times M skew symmetric matrix, and M perp is the matrix that spans the orthogonal complement of the column space of M. And B here is an arbitrary N minus M times M matrix. So to give you some intuition, if I make M equal to 1, if I reduce the Stifel manifold to the sphere, then this becomes a 1 times 1 skew symmetric matrix, which is identical to 0, right? A 1 times 1 skew symmetric matrix is always 0. And then you get just M perp times B, which is the parameterization of the tangent space of the sphere. It's the orthogonal, the matrix that spans the left null space of M multiplied by N minus 1 times 1 vector, right? So this is just the parameters when this term is 0. This is just the parameterization of the sphere. On the other hand, if I make M equal to N, if I work with square matrices, now M is full rank, and M perp is now 0. And I get M times a skew symmetric matrix A, which is the parameterization of the special orthogonal group. So M equal to 1 gives me back the parameterization of the unit sphere. M equal to N for a square matrix gives me back the parameterization for the special orthogonal group. And the nice thing is that given a point X, I can recover those matrices A and B very easily, just multiplying X by M transpose and by M perp transpose. And once I have the matrices A and B, I can now, once I have the matrices A and B, I can now map the free entries of A and B into the Euclidean space. So basically, a point here on the tangent plane to the Stifel manifold is parameterized by the free entries of A and the free entries of B. And the sum of the number of free entries in each of those two matrices is exactly the dimension of the tangent space. So it runs exactly like before. If I have a set of particles that represents the posterior at instant k minus 1, I can compute again the centroid of the particles. So this is exactly the same algorithm as before, except that I'm replacing the exponential map and the log map with retraction and lifting maps, because for the Stifel manifold, I don't have an analytical solution for the exponential map and the log map. So instead of using exponential and log, I use retraction and lifting. So I compute the centroid, then I do the lifting of the particles to the tangent space. I extract now the corresponding parameterization A and B for each particle. For each particle, as I explained before, and now I fit a Gaussian to the parameters of A and B. I transmit that Gaussian to the remote node R, and then the remote node R resamples from the Gaussian and reconstructs a point on the tangent space using the centroid and using the mapping between the Euclidean space and A and B, and now does the retraction to the manifold to get points back to the manifold. So yeah, it's basically like this. It's a little bit more complicated if you want to do fusion. It's a little bit more complicated because you have to represent all the distributions on the same tangent space. And in this case, we use the tangent space, which is again the mean of the means. And you have to do basically the parallel transports of the distributions from each of the local tangent spaces to this common tangent space to do the fusion. In the interest of time, I will skip this. And let me just move to some numerical results, perhaps. Okay. So basically, this is an example where we have this simple network with 5 nodes, and the nodes are tracking different states. In this case, the states are defined on the L sphere, and in this case, they are defined on the Stifel manifolds. And what you can see here is that the proposed manifolds particle filter matches basically the centralized solution. And it's much better than both ATCs or Rendex EKFs that ignore the geometric constraints. So these are ATC and Rendex EKFs that track the states without the geometric constraints, assuming that the states are Euclidean. So you can see that they are very bad. And also the isolated particle filter that tracks the states on the manifold but does not do cooperation is also worse. So basically the gap between those two curves is the advantage of the cooperation, and the gap between those two curves here is what you gain by incorporating the geometric constraints. And also by using sequential Monte Carlo instead of Kalman filtering, so to handle the nonlinearity. It's more or less the same thing here for the Stifel. And those are examples on the special orthogonal group, on the special Euclidean group. I didn't show you the observation model for those two cases, but basically you are observing rotations around a fixed axis. So you have a fixed axis at each node. We will know the fixed axis, and you observe a rotation for the special orthogonal group. And in the special Euclidean group, you observe a rotation plus a translation. And the rotation and the translation are evolving slowly over time according to that random walk. And again, you get a performance that is close to the joint centralized particle filter. It also matches the likelihood consensus particle filter, the one I mentioned back in the first slide, that is fully distributed but simulates the ideal optimal centralized filter. And it's again better than the Euclidean EKFs. And in this particular case, it's also better than manifold constrained Euclidean common filter. So you can also design manifold constrained Euclidean common filters. So there is a gain from the use of the geometric constraints, and there is also a gain that comes from replacing EKF with particle filter. So basically, that's what I had to show. I introduce particle filters to track a sequence of states that evolve on non-Euclidean manifolds. They employ Gaussian approximations of the weighted particle set that are defined on the embedding of the tangent spaces. They have low communication costs and are fully distributed. And the simulation results show that the performance surpasses or equals that of alternative methods. Of course, there's a lot of future work to do. One of the things that would be very nice to do is to derive theoretical performance bounds for Bayesian filters on those manifolds of interest. So if you could derive things like posterior Kramer-Howell lower bounds for that dynamic state space defined on the manifold, that is an interesting problem. It's a tractable problem actually, because if you think of deriving PCLRBs for generic nonlinear state space systems on Euclidean space, normally you are able to get a recursion for the Fisher information matrix. The recursion may depend on expected values of Jacobians that cannot be computed analytically, but you can approximate those expected values using Monte Carlo simulation and get a numerical estimate of the evolution of the Fisher information matrix. In this particular case, you can do the same thing, but you have to compute gradients or score on the manifold, which is a little bit more involved. But I believe it's possible to obtain a recursion for the Fisher information matrix similar to the one that you get for the state space models defined on Euclidean states. So that's one of the things that we would like to do for matrix Lie groups and for Stifel. And then, of course, we have to understand better the convergence properties of this algorithm. Okay, so that's it.